live.
Hello, everyone. Welcome to our Astronomy State of the Art live Q&A session with Professor Chris Impey. I hope everyone's having a good morning today. We've got a lot of questions to go through already, but I will let Chris introduce himself really quick before we start.
Okay, welcome everyone to another live session. We're getting little cutouts here at my end and maybe at your end too, so I hope our video and audio work sufficiently well. In any case, the floor is open for your questions.
All right, let's start with one from a live viewer, Richard Tennis. He asks, a new study says the habitable zone of planets is narrower than thought because some regions where where liquid water could exist would have too much toxic gas for survival of complex life. Your thoughts?
Unfortunately, you were cutting out. This could be tough today. So I think I got the question with about every third word missing. The habitable zone is a traditional concept based on the liquid state of water. So it has its inner and outer bounds where water freezes and water boils on the surface of an Earth-like planet. That's immediately moderated by the atmosphere of the planet because the calculation essentially uses the radiation balance of the star's light reflecting off the surface of a planet and the equilibrium temperature. But of course, the gases in the atmosphere can exert a blanketing effect or a greenhouse effect. On the Earth, that amounts to about 17 or 18 degrees C on average across the planet. And so the Earth is warmer than that simple calculation would say by that amount. And other planets will have alterations in the same way. They may have more carbon dioxide and more greenhouse warming, and so be warmer than you would calculate based on their distance from their star. So the habitable zone is already a flexible concept because it has to depend on the atmosphere of the planet, and in most cases that's simply not known. And it's also a probably inappropriate concept because we know that life can exist on Earth below the freezing point of water and above its boiling point. And we suspect life can have a significantly large range and also exist with very modest amounts of water indeed, where maybe in deep rock water has percolated through the pore space, but we're not really talking about a liquid medium. So given all of these caveats, the traditional habitable zone concept is just a starting point. It's just a base coat of paint for talking about life on a planet. Really, more detailed information is needed to talk about habitability. And of course, in most cases, for most exoplanets, that information simply doesn't exist. Ready for the next question?
All right. We have a question from one of our email viewers that asks, do gravitational waves interact with each other? And if so, how then do astronomers identify the direction of a particular source?
It's a good question. And yes, gravitational waves do interact with each other. So if you have two sources of gravitational waves, the gravitational waves from the event or the source radiate in 3 dimensions, altering space-time. And gravity waves are what's called tensor waves. So they vary in strength according to the direction, x, y, or z. And they have different modes of variation, of oscillation, compression, rarefaction, and a transverse component as well. So that's quite complex behavior. And so essentially you have to do a tensor addition of the signal of the gravitational wave, the displacement of space-time at any point to calculate how two waves would combine in space. That's not a trivial calculation, but it's certainly doable. Of course, in astronomy to this point, gravity wave sources are quite rare. We've only detected of order a dozen sources of gravitational waves, so we've not actually encountered the situation where multiple sources of gravitational waves interact. And it would indeed make the detection of that signal at the Earth with a LIGO type instrument more complicated if you were dealing with multiple events. So at the moment, it's a hypothetical idea that the gravitational waves from multiple events interact. But of course, in the universe, gravity waves are emitting in all directions from events across space and time, and so they do interact. It's just that we haven't got to the sophistication in our methods of detection on Earth for that to become an issue yet. Ready for the next question?
All right. So another question from email from Christy Reed. She asks, have any more results come out of the dark energy survey regarding dark energy getting stronger? And what's your view on any of these results from the survey?
Sorry, Vicky, you have to repeat the question. Some critical words dropped out.
Of course. She asked, have any more results come out of the dark energy survey regarding dark energy getting stronger?
Right. Well, first of all, hi, Christy. Christy is a very important person to us in our Coursera course because she's one of our mentors and she's been a stalwart supporter of the course for years. So everyone online should know who Christy is, even if you haven't encountered her directly. But if you've been on the discussion boards, you may well have encountered her. The Dark Energy Survey is a major survey, imaging survey using the sort of essentially turning a 4-meter telescope in Chile, the Sartolala 4-meter, into a dedicated survey instrument. And it's observing a substantial swath of sky with really high precision, looking at the shapes of galaxies and measuring their redshifts in a photometric way by looking at different wavebands. And it's basically trying to map out the growth of structure and the shapes of galaxies as a way of seeing potentially if dark energy manifests at different strengths in different directions or at different look-back times or redshifts. How this might manifest is in the growth of structures. So since dark energy works in opposition to gravity, gravity is forming structures like clusters of galaxies on all scales, and dark energy will actually sort of slow that process down. So if dark energy varies in its strength from direction to direction or over cosmic time, then astronomers could in principle detect it by a change in the rate of structure formation or the presence of the largest structures, for example, at a given time. The survey is not close enough to completion, and it would probably take its full data to even do this analysis. So I think the astronomers have not yet done this kind of analysis. And even if they did have all the data, it's a very challenging signal to look for. So at the moment, there's no evidence of dark energy varying in time or space. It seems to be the very simplest manifestation of the phenomenon, consistent with Einstein's cosmological constant. Ready for the next question?
All right. Rana Mudasar asks, why do the outer gas giant planets rotate faster than the inner terrestrial planets?
They don't actually all rotate faster than the inner planets. For their size, of course, they do, and that, of course, reflects a high amount of angular momentum. So there's a lot of angular momentum out in the outer part of the disk when the planets form, and that angular momentum, as the gas giants collapse, representing a lot of material, Jupiter and Saturn in particular being hundreds of times the mass of the Earth, manifests into a large angular momentum of those planets, and that is a large amount of rotation. So the reason why they rotate so fast is based on the initial conditions. It's actually set down by the way the protostellar disk was rotating when it collapsed 4.5 billion years ago. So this is not a mystery particularly to planetary science, and we would expect these phenomena to play out in other parts of the universe and other solar systems as well. Ready for the next question?
All right. Another question from email. One of our viewers asks, the size of the observable universe is quoted as 93 billion light years, and the unobservable universe is theorized to be much bigger than that. How did scientists arrive at these huge numbers?
The number 93 or 92 billion light years, which is a diameter, so in any direction, it's half that number, comes from a calculation that involves the best measurements of cosmology parameters. So in the universe that we measure with dark energy and dark matter, you can calculate what the history of the expansion rate is over the age of the universe, all close to 14 billion years. And what is key in this calculation is that early in the expansion, the first 4 or 5 billion years, in fact, any 2 points were moving apart at faster than the speed of light. In other words, the universe was expanding superluminally, faster than light speed. There's not a violation of relativity because it's only special relativity, a local inertial frame calculation that has a limit of the speed of light. General relativity governs the expansion, and there's no speed limit in general relativity as to how fast a universe can expand. So we had the situation that points in space-time were moving apart faster than light speed, which is how the universe can be more than the sort of intuitive number of 14 billion light years in every direction. You'd imagine if it's 14 billion years old, you couldn't see further than 14 billion light years in any direction. And that factor ends up being about 3. So from 14, you get up to about 46. And then double that for the diameter is 92. So that's how this huge number for the observable universe comes about. And it doesn't represent the physical edge, as the questioner implied. The physical universe could be much further. The limit of 92 billion light years in diameter reflects the regions of space-time which we can have seen in the history of the universe, 14 billion years. As time goes by, we see more distant regions of the universe. And so over time, played out forward, the observable universe will get steadily larger. How much larger the physical universe, all that there is very uncertain because we simply don't know what the underlying space-time was at the point of the Big Bang. And so that physical universe number is not known to cosmology or to astronomers. It's not even really diagnosed by observation in any way. Ready for the next question?
All right, so we have a question from one of our younger viewers. Amelia, who's 7 years old, wants to know, why are there holes in the moon?
Okay, Amelia, good to get a question from a young person. I'm glad you tune in, and I hope you check out the course. I'm pleased that you're challenged by the material and willing to go with it. Holes in the moon. The moon is a very interesting looking object. It's splattered with features and craters and radial marks that come away from the craters and dark areas that were called mare, which is Latin for sea, because hundreds of years ago, before we knew the moon had no atmosphere and no water, people thought they were literally seas, oceans. So the moon has some very interesting structures. The things that look like holes are actually craters. So because there is no air, no atmosphere to burn up things that fall in, the moon has been subject to impacts in the solar system for 4.5 billion years, more especially in the first half billion years. The impact rate has tailed off. And those big impacts from objects that may be tens or hundreds of kilometers across have left huge craters in the moon. Those craters are much bigger than the object that hits them. So the object that comes in is carrying so much energy that it creates a hole much bigger than itself. It's vaporizing rock. The rock almost liquefies and spreads out in a wave away from the impact, and that's what leaves this hole in the moon. That's not a very deep hole, actually. So the depth of a crater is a small fraction of its diameter. But we can see shadows of these craters. If you look at the moon when the illumination is oblique or at an angle, it's very easy to see the shadowing of the craters with a small telescope. And satellites have seen this really clearly. So the moon has very interesting structure. No actual holes, but a lot of big dents and craters caused by impacts over cosmic time. Ready for the next question?
All right. So Akanksha Rani asks, it is said that if we travel by the speed of light time, we would stand still. Why is that?
Okay. Did you cut out, or is that the end of the question?
Oh, I'm sorry. That might my mic might have cut out. Or well, so she asks, it is said that if we travel by the speed of light, time would stand still. And why is this?
Well, this is actually a nice question because it alludes to a very lyrical way that Albert Einstein, as a young man, when he was thinking about light and coming to the theory of relativity, he thought about it. He mused with his friend Marcel Grossman, a young high school kid that they studied physics with, what would the world look like if I rode on a beam of light? Because he knew light was the fastest thing there was. In physics, that was well known. Nobody at the time knew that it was an absolute speed limit. And that thinking of what would happen if I rode on a beam of light, what would the universe look like traveling at light speed, impelled him towards the very profound theory of special relativity. In fact, the only thing that can travel at the speed of light is light itself, electromagnetic radiation. And so electromagnetic radiation is the only thing that can travel that fast. If any other object tries to move that fast, mostly subatomic particles, big physical objects can't be made to move anything like the speed of light, then relativity says that their mass will increase, their inertia will increase, and they will resist a change in their motion, so they will never actually reach the speed of light. So the question is a hypothetical that can never be achieved, because only light can travel at light speed, and so all other components of the universe are destined to see the universe where they can move fast, but they're not ever going to move at light speed. Ready for the next question?
Okay. Predrag Ivasev asks, is it possible to create experiments or observations to find out if we might be part of a multidimensional time space as per some multi-universe theories?
So the question of whether there are more than the three dimensions of space and one of time that are the standard theory of cosmology and relativity is an interesting one. The idea of multidimensional space-time comes from two directions. It comes from string theory, which looks at the deepest states of matter and their fundamental nature, and it makes the most sense in a mathematical theory that has 9 or 10 dimensional space-time. So there are hidden dimensions. Those dimensions are compactified in that jargon of the theory, and only accessible on incredibly large energy scales that we can't achieve ourselves. So they're invisible to us. So one answer to the question is, can we manifest these extra dimensions within nature, as string theory would predict? And the answer is no, we can't, because the energy scales implied in string theory are just so phenomenal. They are very, very, very far beyond any technology we have access to. Now, if multi-dimensions exist, they could also be part of the construct of the universe and the emergence of our universe from a larger situation of space-time that does have multiple dimensions. And the question is, could that be detectable with an astronomical type observation? And the current answer is no, because in part because the theory is not well enough formed to make a directly observable prediction. And in part because of the catch-22 that we are trapped within our three-dimensional space plus one dimension of time. And so in principle, it's hard to imagine how we could access a hidden dimension, given that our observations are made in 3 dimensions of space. Ready for the next question?
Okay. Varun Singh asks, is it possible to convert infrared long-wave radiation into short-wave radiation? They think it might be a possibility of, converting that to reduce global warming, converting infrared into shortwave.
So, different forms of electromagnetic radiation have energy, wavelength, and frequency that are simply related. And we have the abilities to create electromagnetic radiation of enormous range of energies. To convert one form of radiation into another at a different energy will, of course, require energy, because if you're going to convert, especially a longer wavelength radiation, into a higher wavelength radiation, you somehow have to add energy in the process, and that implies an interaction with the radiation to boost its energy. Combining photons is a simple and trivial way. Somehow letting the radiation harvest the energy of particles is another way, and there are microscopic mechanisms to do this. But you're going in the wrong direction, essentially. It requires energy to make this happen, so it's not a natural thing. It's far easier to go in the other direction in nature, of going from short wavelength radiation to longer wavelength radiation. A simple example involves emission and absorption of photons by a planetary surface. So when photons arrive at a planetary surface They are down scattered, if you like, in their interactions with materials and solids to longer wavelength radiation, like infrared. And that's the heat radiation that comes off a planetary surface, when in fact mostly it's being illuminated by light. The trapping of that heat radiation leads to the greenhouse effect, of course, where the visible light can escape, but the longer wavelengths that have been created in the scattering can't escape. So we have many more examples in nature of the higher frequency or higher energy radiation transforming through a natural process into longer wavelength radiation. Ready for the next question.
All right. Alejandro Torres asks, is it true that antimatter could be considered the fuel for the future of space travel? And how efficient is it compared to chemical energy and nuclear energy?
Antimatter is, of course, would be a holy grail of space travel, of propulsion, because it's the most efficient energy process possible. It's 100% efficient, essentially, because if you can harness and harvest and contain antimatter and then in a controlled way make it annihilate with normal matter, the entire energy, mass energy, mc squared, is released from the matter and the antimatter. So it's 100% efficient. And so it's vastly more efficient than chemical energy. Normal fusion, stellar fusion, is about 0.7% efficient in the sun. So it's more than 100 times more efficient than stellar fusion. Stellar fusion is hundreds of millions of times more efficient than chemical energy. So antimatter energy is billions of times more efficient. So, it's phenomenal. Obviously, that's why it's attractive. The challenges, of course, in the technology of making antimatter work as a propulsion system are enormous, because antimatter is, on Earth, actually the most expensive thing there is. It would cost, if you scaled up the way it's made in accelerators and physics facilities, antimatter, if you could buy it on the shelf, doesn't really make any sense because you can, would be billions of dollars per gram. It's just very hard to make more than the tiniest amount of antimatter. So as efficient as it is, we don't really have a technology for producing it in significant quantities. And that, of course, would be required. And in fact, in a future scenario where we're traveling in space, you'd want to create the antimatter in a vacuum situation beyond the Earth orbit. So you'd actually have a deep space antimatter creation facility where the normal matter, is very regulated. You have a containment system for the antimatter, and there's no other matter there because you're in the vacuum of space. Nobody's even come close to designing a technology that would do this. So if I had to guess, antimatter drives of the stuff of science fiction are still hundreds of years away. Ready for the next question.
All right. Debaparna Goswami asks, why don't all galaxies have the same amount of dark matter?
All galaxies have pretty much the same proportion of dark matter to normal matter. So there's almost a universal ratio of 6 to 1, roughly 6 to 1, between dark matter and normal matter for a galaxy. And that fact is also interesting because it has to be part of the galaxy formation process. They do have, of course, very different amounts of dark matter because the overall mass of the galaxy is part of a spectrum of galaxies, and the galaxy luminosity function, it was originally called because we could measure the light of the galaxies before we knew they had a lot of dark matter, is a power law. And that means there are many more small galaxies or low mass galaxies for every large galaxy. So the proportions of dark matter and normal matter scale similarly for galaxies of all types, but galaxies themselves have very largely differing amounts of dark matter. For instance, the Milky Way has a total mass of something close to a trillion solar masses, again, 75 or 80% of which is dark matter. But there are galaxies that are hundreds or even thousands of times smaller than that. So they will have dark matter contents of maybe getting as low as a few 100 million times the mass of the sun. That's the tiniest dwarf galaxies. But every galaxy, except for a few spectacular press stories, most of which have fizzled out with further work, it seems that every galaxy we've found so far, however small, has some dark matter. Ready for the next question?
Okay. Ben Luck asks, how far would we have to travel to start seeing repetitions of galaxies in an infinite universe?
So repetition of galaxies would only happen in a universe that had a closed geometry, and so a topology of space-time where light traveling for an infinite amount of time, if it was old enough, would start to wrap through the universe, multiply travel through the universe. In that way, you would end up with multiple images of the same galaxy, sort of mirages, if you like. So that's indeed a possible scenario. It's possible that the space-time that we observe, where light has reached us in the finite time, which is the age of the universe, is part of a larger construct where radiation could have been traveling for a much longer time, preceding the Big Bang, and where the space is wrapped in a way that light can travel. So these are called, some of these are called small universe scenarios, because the small universe just reflects the fact that the light has traveled through that space-time multiple times and created multiple images of the same galaxy. There are very good pattern recognition algorithms now that can be applied to galaxy surveys to extremely sensitively look for the same patterns of galaxies, not the same very individual galaxies at large distances. They're kind of anonymous blobs, really. But to look for evidence of light wrapping around a universe and creating multiple images of galaxies en masse. And we've no evidence of that. So that theory has not been completely refuted, but there's no evidence to support it at this point. Ready for the next question?
All right. Speaking of galaxies, Jenny Chung asks, how does looking at distant galaxies allow us to look back in time?
Well, distant light is old light, essentially. So the finite speed of light means that the further out we look in space, the further back we look in time. In the solar system, this is a modest effect. We all remember the little time delay of communication with the astronauts who went to the moon, a second and a little bit over a second in each direction. And light takes 4 or 5 hours to reach the edges of the solar system. Light, of course, to the nearest stars takes a few years. Proxima Centauri is just over 4 light years away, which means we see it as it was 4 years ago. So that light is 4 years old. And by the time you get to the outer part of the Milky Way galaxy, that light can have traveled for about 100,000 years. So that's how old that light is. And so on through the universe. As we move to the more distant galaxies, the nearby galaxy is Andromeda, 2.25 million light years. So we're seeing it as it was 2.25 million years ago, when humans were very primitive, not modern Homo sapiens had not yet existed on the Earth. And to the most distant galaxies we can see with the largest telescopes, that light travel time is 11 or 12 billion years, which is a good fraction of the age of the universe. And so simply by looking further in space and deeper, which tends to mean fainter, so you need larger and larger telescopes, you look back in time. Telescopes are like time machines. It's an amazing thing about telescopes and cosmology. And at the limit of our vision, say with the Hubble Space Telescope, and with the biggest ground-based telescopes that are now 10 meters in diameter, we've seen galaxies within 5% of the age of the universe, of the beginning of the universe. So 95% of the time back to the Big Bang, which is pretty amazing. Ready for the next question?
All right. David Santiago wanted to know what effect does the sun have on our weather, specifically with things like solar cycles and, bigger sun phenomena, I suppose.
Yeah, the sun has a big effect on our weather in many ways beyond the solar cycle itself. NASA has a major research program called Living with a Star, and it's funded dozens of research projects over the last decade for people who are trying to understand the effects of the sun on Earth's weather, and also try and understand star activity of different types of stars and see how that might affect their planets, now that we know there are planets around all sorts of stars. So we experience sun weather, but other planets, other Earth-like planets, people on those planets, should they exist, will experience other weather from other stars. Our star is a middle-aged star and a modest-sized star. It doesn't have extreme activity. So the biggest impact on us, of course, is the solar cycle, the sunspot cycle. And even though sunspots cover a small fraction of the sun and don't really change its appearance very much, the high energy radiation, the high energy tail of the sun's radiation varies by a much larger fraction, by 10 or 15%. And so that cosmic ray flux that hits the Earth and interacts with the magnetosphere creates things like the aurora, but also in extreme versions of solar weather can interfere with telecommunications. The biggest danger to the Earth, it comes from something called a superflare. So we've seen pictures of the prominences and flares from the sun's surface. And when those are pointed in our direction and the radiation from those flares comes to the Earth, that can interrupt communications on the Earth. They travel in the aggregate at less than light speed, so we actually do get some notice of this, close to a day. A superflare is a phenomenon that we don't think happens more than every few hundred years. And a superflare is a situation where the sun's high energy radiation varies by an order of magnitude or more, a factor of 10. And that effect on the Earth is dramatic. There was in the middle of the 19th century, there was a superflare that essentially knocked out the then quite rudimentary electrical grid of the northeast part of the United States. And that wasn't the strongest superflare that could happen. Theories predict that the big superflares happen every few thousand years. It just hasn't happened during the time of modern technology, but it would be catastrophic to our communication systems. It would essentially take down the entire electrical grid, destroy sort of communication systems, and actually even frying circuitry in satellites that do telecommunications. We wouldn't really get much of an advance warning of a superflare like this. So that's the thing that people have their eye on in a nervous way, knowing that the sun, while it's benign and life-giving for the most part, has the ability to really mess with our modern technology and our world if we happen to have a superflare. Ready for the next question?
All right. One of our viewers wanted to know, since science education and literacy is lagging behind in the U.S., how can we improve the communication of science to the masses?
Well, it's a good question, a big question, something I worry about a lot and try and do something about when I can. The skepticism and the pushback against science that we see in the United States is unfortunate. It's misinformed, obviously, and it's very counterproductive since science is a generally positive force in our culture. It's also seen elsewhere. I'm working in the UK for a while, and in the United Kingdom and in Europe, there are similar things happening. There's some skepticism about science. There's a generally low level of science literacy. So basically, some fraction of the population is really interested in science, pays attention to the news about science, is convinced that science is a positive force in our society, and fine. Those are the people who already are on board. The real issue, and then there's probably an equal percentage, and maybe it's small also, like 10% who are kind of virulently anti-science. There may be climate change deniers. There may be people who willfully do not accept the evidence that vaccines are safe statistically and that do not cause autism and so on. So they buy into some of the wacky ideas about diet, nutrition, and health and so on. It's in the middle that the opportunity for science communication comes, and that's from people who are generally mildly benignly disposed towards science, but not super informed about it. And so I think that's where science communication can have its best impact. And to do that, is not trivial. You have to present science in a very appealing way. You can't blind people with jargon. You can't speak at too high level, but equally, you can't talk down to them. You have to engage them in a conversation, make it appealing, not hide the power, which sometimes means the complexity of modern science, but show that it's answering very simple and profound questions about our existence and the nature of the universe we live in. And the more people that do that, scientists, of course, all should be doing it, but also people who like science and know about it. There's plenty of members of the public like that, should all be helping with this effort and using every means possible, including, social media, blogs, TVs, small, short videos that everyone can put up on YouTube, and so on. Ready for the next question?
All right. So we have a question about kind of similar to the astronomy education question or science education question we just addressed. Debaparna Goswami wanted to know, is it possible to pursue a career in astronomy with a master's in engineering physics without going for a PhD? And I guess we can expand that to, pursuing a career in astronomy with a master's in any sort of engineering or science that isn't physics and astronomy.
It's a good question, and it's become more possible than it used to be. The path to astronomy research and PhD and beyond used to be very strictly defined. I went through physics as an undergraduate, and most of my colleagues and my peers did. So the first degree for someone who wants to be a professional astronomer or do a PhD in astronomy is almost always physics. And that makes sense because when you're a graduate student in astronomy, you have to take a lot of coursework, and probably 2/3 to 3/4 of that coursework is physics. I mean, it's astrophysics, but sometimes it's just physics. So there's a lot of overlap between the two fields. That said, however, it is possible for people who are trained in a technical field, and that would be any engineering field, and mathematics, of course, is also possible as a path, or other related fields like chemistry and biology to a lesser degree. It is possible to move into astronomy from these fields, from engineering and from life sciences. It's more challenging because you still have to get a base coat of paint of physics up to the level of sort of senior level physics courses. Not every physics course is necessary. You need electromagnetism, you need thermodynamics, you need quantum mechanics, you need those basics, 4 or 5 of the basic physics courses. You don't need the full suite of physics courses. So the answer is it is possible. Not all programs are flexible in how they define their admission criteria for people taking an advanced degree. But at Arizona, for example, it's a minority, but we've had students who've transitioned from other fields, and including some who've come from an engineering background. It's possible, but you are going to have to take some extra courses, so it'll extend the time of a master's degree or PhD. Ready for the next question?
Okay, so 2 of our viewers had questions about the James Webb Space Telescope, so I kind of combined those. So they were wondering, what's your opinion on the James Webb, and how big of an improvement in observing power will it provide? Like, what sort of research will be possible that isn't possible today with things like Hubble?
Yeah, so the James Webb Space Telescope is the biggest game in astronomy. It's also been called somewhat pejoratively the telescope that ate astronomy, because its budget is officially 8 or 9 billion, heading towards 10 billion by the time it launches in October 2021. It's had vast cost overruns. It's been more complicated and difficult to get built than anyone possibly imagined. It's a very challenging mission. So the opinion of the James Webb, even amongst astronomers who love the idea of it, is a little mixed, because it's killed other projects, essentially. It's made other missions not possible with the finite resources that NASA has or the federal government has for funding research. So that's a little hesitation about being completely gung-ho about it. But in terms of its capability, it's a transformative capability. Remember, the Hubble Space Telescope was limited in size by something that would fit inside the bay of the space shuttle, which launched it. So this mirror is just a little over 2 meters in diameter. James Webb is 6.5 meters in diameter, so it's an order of magnitude more light gathering power than any telescope we've ever put in space. It's also going to a distant location at a Lagrange point, which is a very pristine environment for observation. The Hubble Space Telescope, as good as it is in low Earth orbit, which is a kind of messy environment. There's debris there, there's air glow, there's scattered radiation from the Earth, of course, coming upwards from the surface of the Earth, even on the night side. And James Webb will not have any of that. It'll be in the probably best space environment you can have for a telescope. It's skewed a little bit towards longer wavelengths, because it was impossible to make a mirror that size of the same optical quality as the Hubble telescope for short wavelength observation. So much of the James Webb science is tilted, if you like, towards longer optical wavelengths in the near infrared. Within that, there's many things it can do. It can observe all the standard things that Hubble can observe with 10 times the light gathering power. Distant galaxies looking for first light, clusters of galaxies, the shapes of galaxies as an indication of dark energy, the clusters of galaxies and the way they grow in the early universe as a measure of dark matter and other aspects of structure formation. It can do exoplanet research. It can look at stellar evolution and probe into supernovae with those long wavelengths. So many kinds of astrophysics. In fact, almost everything in the topic table of astronomy will be done by the James Webb. Ready for the next question?
Okay. So Styles Hoot Owl asks, do you believe that there's a ninth planet beyond the Kuiper Belt?
Well, there's likely to be Pluto-sized objects, Kuiper Belt objects now. We think that there are a significant number of objects like that in the Kuiper Belt. The Kuiper Belt, just for reference, is a region that extends from about 40 to 80 astronomical units, so beyond the orbit of the traditional 8 planets. Pluto is presumed now to be a captured object. It's on a highly elliptical orbit, an inclined orbit, and it shows strong interactions with the outer planets. So it's likely to be captured from the Kuiper Belt. And so in the deeper parts of the Kuiper Belt, which means they're pretty faint and hard to detect if they're especially a bit smaller than Pluto, is likely by some estimates that there are between 4 and 6 Pluto or close to Pluto-sized objects out there, Planet 9 if you like. So there is going to be something like a Planet 9 and maybe a handful of them. It would be surprising or unlikely for them to be much larger than Pluto, but they could be similar size. Ready for the next question?
All right. And just as a heads up, I think this is going to be our last question for the day. So Alexander Zaleski asks, are there any individual stars located between the galaxies of the local group?
I missed a critical part of that question. Are there any stars?
Are there any individual stars located between the galaxies of the local group?
Okay. So that is a good question. Galaxies sort of tail off into space, so the edge of a galaxy is not a sharp boundary. In the Milky Way, which is in the local group, Andromeda in the local group, as the 2 large galaxies. Andromeda has a dwarf companion, M33, and then we're left in the local group with just a few dozen dwarf galaxies. And these galaxies are contained within a box, if you like, that's about 3 or 4 million light years across. So those galaxies have edges, but the edges tail off into deep space. And the question is, can stars be found between these galaxies? And almost certainly there are stars in those regions. And just a couple of interesting cases have been found. Now, of course, they're going to be very faint. An individual star at a distance of 1 million light years is extremely difficult to see. But the reason that we believe they exist is based on simple dynamical models of galaxies, which show that stellar interactions can often give one of the members in a violent interaction, where they don't collide, but they have a very close passage, can give it a large ejection velocity, essentially a velocity that's beyond the bound velocity of a galaxy. So the Milky Way, that velocity is about 250 kilometers per second. A star with substantially more than that velocity will leave the galaxy. And if that happened a while ago, it will have drifted into intergalactic space. So theory and simulations definitely predict the presence of intergalactic stars within the local group. A couple of claimed examples have been found, but the evidence, unfortunately, is not good enough for them to go in the books as real intergalactic stars. So that's a research project that actually is very active and underway, and we might see some results of that in the next few years. Thanks for all your questions. That's the last one for today, and next one, actually, I will move countries again and be not in the UK, but in Italy, where it is a genuine summer. Here in England, it's kind of a half-assed summer with the sort of temperature of 70 degrees, 65, raining, windy sometimes. And where I'm going in Florence, it'll be pretty hot, although not Tucson hot. So we'll reconvene in 2 weeks, and I'll see you then. And thanks to Vicky and Alexander for facilitating this session. Goodbye.